Let's go over assignment 1 for chemistry, Lmmu Mathematical University. So here is the first question. In less than 210 lines, define the following. And the first one we want to define is an exact number. What is an exact number? Now, an exact number is just a number that is showing you terms which are exactly known, or an exact number of value that is known with certainty. What is an exact number? It is a number that is known with certainty. In other words, you are very sure. And numbers that you are very sure about are things that you have counted. For example, the number of people in a room, we are really sure if we count. So things that we count, we really know them. So those are going to be exact numbers. Now, things that you measure are not going to be exact. So a measured number is a number that is obtained from measurement and it has got some degree of uncertainty. For example, I'm going to get something like this. Let's say I get uh, a wood that is this length. I'll ask one person to use a ruler to measure it. One person might measure it to be 2.01 centimeters. Another one can maybe say come and measure 2.02 centimeters. So you see that the last number here is uncertain. Different people find it differently. So that is a measured value or number. It has got some uncertainty. How about accuracy? Accuracy is how close a measured value is to the true value. For example, if the true value is supposed to be 2 and then I measure 1.9 or I measure 2.1, these two values are close to 2, so I am accurate. And we can also use this example if you've watched in movies where people are throwing knives. So if someone throws a knife and it comes to hit on this very middle or very close to the middle, let's say the knife reaches there, that person is accurate. So the more you go away from the true, the more inaccurate you become. Now, precision is how close repeated values are to each other. For example, I measure 1.9 at the beginning, and then next I measure 1.91, and then I measure 1. Let's say 89, and then I measure 1.90. You can see these values are very close to each other. So how close repeated values are close to each other, that means that I am accurate. I mean, I'm precise. Now, being precise doesn't mean you always be accurate. Say, for example, someone throws a knife, it hits here. He throws a knife, it hits here. He throws a knife, it hits here. He throws a knife, it hits here. He's throwing almost at the same point, meaning that this person is precise. But then it is not near the true value or the value that you want. So meaning that this person is not accurate. How about random errors? What are random errors? Now, random errors are basically errors that cannot be predicted, unpredictable variations in measurement. Okay, you can't predict them, and these ones are mostly going to be caused by changes in the environment or the instrument has got limitations. Let's say, for example, want to measure the volume of a fluid. And then the cylinder that you are using, the number showing here says 21. The number showing here is a 20. It will be very hard for you to be able to measure the exact value there because you just say, okay, since this number is between 20 and 21, it can be 20.5. But if you use something that is more accurate, you might find that maybe it was actually supposed to be 20.51. So there is limitation because of the instrument that you are using that produces random errors. Or maybe there is a limitation in the environment. Say you are trying to measure the weight of, say, an object. And here is your beam balance. You are trying to measure something, you find that its weight, say, is 8.51. But really its weight is supposed to be like 8.40. That might be due to the wind in the environment, and that is raising the weight of your object. So that is a random error, and you can't stay away from it because it's part of the environment. Now, a systematic error is an error that is going to be seen when there is actually a problem with the calibration of the instrument. Okay, there is a problem with actually the instrument instead of the way it has been calibrated, or there is improper experimental design. So, for example, say here is your cylinder. Here it is reading 20. Here it is reading 19. Say here it's reading 30. You can see just the way the cylinder has been made, it is wrong. So if you see something maybe somewhere here, you might come and read, let's say, 30. Even if you give another person, they'll still read 30. Another person will still read 30. The problem is not with you who is handling it. The problem is with with the calibration of the instrument itself. So that will lead to a systematic error. But a random error, the more you avoid random errors. For systematic errors, even if you try, you give a different person to try, you still find the same error. How about an absolute error? Absolute error is just the difference between the true value minus the recorded value. And actually, you take the absolute value of that. The absolute value of the true value minus the recorded value. So let's say the actual mass of the calculator is 20 grams, and then I record 19.6. What would be the absolute error? It's 20 minus 19.6, that would be a 4. Even if we subtract 19.6 minus 20 to give you a negative 4. But absolute means that the answer should always come out positive. So the absolute value of negative 4 is still positive 4. So that is it for that question 1. And then question 2, give 3 examples of exact and measured numbers you are likely to encounter in chemistry. Write down 3 causes of random errors and also systematic errors. What are some causes of random errors and systematic errors? Now, to start with the first part, 3 examples of exact numbers that you'll be able to encounter in chemistry. Exact numbers that you encounter in chemistry include numbers like the Avogadro's number, which is 6.022 times 10 to the power 23. This is an exact number, and this number represents the number of atoms or molecules or particles or ions which are present in one mole of a substance. Another number that you are going to be able to encounter is called Planck's constant. So this is the Avogadro's number. The other number is Planck's constant, that is 6.626 times 10 to the power negative 34. Okay, this is actually in joule second, that's a unit. This is Planck's constant. Another number that you encounter is the speed of light, which is like a 2.998 times 10 to the power 8. These are some exact numbers that you'll be able to encounter. So that's that's the first part of the question. Exact measured numbers you are likely to encounter in chemistry. Write down the 3 causes of random errors. Now, what are the causes of random errors? Random errors, as we said, the problem is not with you. The problem is actually you can't stay away from these mistakes. For example, they can be instrumental limitations, imperfection in measuring instruments. All right. For example, I gave an example of a cylinder. If it's reading 19 here, here it's reading 20, and then the reading ends here. Someone might actually 20 on top and then 19 down. Someone might just say 19.5, but maybe the exact number is supposed to be 19.52. So that is the instrumental limitation. Other causes of random errors includes environmental fluctuations. There is a change in temperature, change in air, conditioning, change in wind, also human variability. Okay, it's also going to be able to cause some kind of random errors. So for example, one person can come here and say, ah, I think it is 9.5. Another one will come and say, okay, maybe I think it's 19.6. Another one will say, ah, this is 19.51. So depending with human who is doing that measurement. Now for systematic errors you can't avoid. You It's a problem with the system that you are using actually. So some of the causes is calibration of the system is wrong. Okay, that's the first thing, calibration. Another thing can be bias. Okay, whereby you have got a preconceived notion affecting measurements. There is already something that you there is already something that you are concentrating on. In other words, you are biased. You are just trying to concentrate on one end. That's the meaning of biased. Trying to concentrate on only one portion. So that will lead you to measuring wrongly. Also, experimental design flaws. There is something wrong with the way you have designed your experiment. And so, whatsoever you do, everything, the answer will always be coming out wrong because of the problem in the experiment. Number two, for each of the following quantities, underline the zeros that are significant and determine the number of significant figures in each quantity. So if you see a number which has a decimal and there's a zero at the end of a number that is not a zero, that zero is significant. For example, this zero here is significant. For this number, it has got only two significant figures, the 3 and the 0. And then for this number, any zero that is between numbers is significant, but not in front. So this zero is significant, we've underlined it. So this number has got four significant figures. For the next one, all zeros which are between numbers are significant. So this zero is significant. So how many significant figures do we have? Every number, as long as it's not a zero, is significant. So here we've got 1, 2, 3, 4, 5. So this one has got 5 significant figures. For this number here, all zeros in front of a number and that number has got a decimal are not significant. So these zeros that you can see, so there's no zero that is significant here. So the only numbers which are significant is 4, 7, 1, and 5. So we have got 4 significant figures. And then for this number, all zeros which come after a number in a number that contains a decimal point, they are significant. So these two zeros here are significant, meaning that 57600 are all significant. So this number got 5 significant figures. And then same with this one, any zero that comes after a number, any number that has got a decimal is significant. So this zero here is actually significant. So this number has got 1, 2, 3, 4 significant figures. Number 3, after drying, mass of sodium tetraborate was determined. 5 times using the same electronic balance as follows. So the mass of this tetraborate was determined, and it wasn't determined once, it was actually determined 5 times. Okay, now these are the masses which were found: 0.35, 4, 0.5, this one, also this one, and this one. Was a measurement error incurred in the process of measurement above or not? Now look at these values. The first one is 0.35. The next one is 0.5. The next one is 0.51. The next one is 0.5, 0.53. So there is actually an error here. Why? Look at this one. At least this one, this one, this one, this one, they are all 0.5. But this one is very far away from the rest, meaning that there was actually a measurement error which was incurred somewhere. So there was a problem for this person to find zero point 0.3 if the others are finding is 0.5. Okay. What kind and likely source of error occurred in this experiment? So the kind that would have occurred, there might have been a systematic error. The balance might have been having problems with calibration, right? A problem with calibration. That is why someone found zero point 0.3 and then started finding 0.5, 0.5. There could have been also some random errors. Random errors, these are the ones which are responsible for these last numbers. Some he found 0.5020, again he found 0.5112, and again he found 0.53. These might be random errors, and also problems with the reading of the instrument. But this is more the setup of the instrument because the deviations are more. If the correct mass of sodium tetrahydroborate was 0.510, select values from the measurement above that are a outlier, accurate, precise. Now to look at an outlier, look at the true value. The true value is 0.501. So outlier is anything that is very much away from zero point 0.5. And you can see 0.3 is so much away from zero point 0.5. So that one is an outlier. And then now a number that is going to be accurate. Accurate is a number that is very close to 0.501. Okay. So if you look at these values, 0.5010 is the true value. Which number is very close to 0.501? So this is 0.502, 0.51, 0.511, 0.5. Okay, let me first write a true value, 0.501. At least 0. At least for a number to be accurate, it should differ with only the last number. Okay, only the last number. So if you look at these values, I've got 0.5020. That is necessarily not accurate. And then the next one, 0.51, not accurate. 0.51, not accurate. 0.53, not accurate. So the closest accurate value that we have here is this one, which only differs on this number. The rest are the same. You look at the numbers in front here, they should be the same. Only a 2 is different there. And then precise. What is precise? Precise is where the repeated values are close to each other. Okay. So if you look at 0.502, 0.51, now 0.502 really not precise. So precision is you are looking at numbers which are close to each other, repeated values. Say 0.510. This is also 0.51. This is also 0.5. Now this is 0.53. So this can't be precise. So at least the numbers that we're expecting to be precise is 0.510 and 0.511, because at least those, they only differ only the last numbers, 5, 1 here, 2 there, and then 1 and 0 here. At least those are precise. Using scientific reasoning, select the 3 values that you would use to calculate your mean mass of sodium tetraborate. Now using scientific reasoning, when you are finding the mean you actually add numbers and then you divide by how many they are. So since the true value is 0.51, the 3 numbers that we can get which are close to this one for us to find the mean is 0.5, 0.5105, 0.512, and at least which one else will be able to make sense here? Okay, and at least 0.53. 0.53, because they should be close, and now 0.53 has just gone too much. At least 0.502. Okay, this one. So at least these we can use them to calculate the mean. Okay, the next question is saying, based on question 3 part 4, calculate the absolute error and the standard deviation in the measurement. the absolute error, and the standard deviation. Now, the first thing that you should be able to find is we need to find the mean. For us to find the mean, the values that we want to use are those values which are accurate. Or I mean those values which are precise, because it's the precise values which we are actually using in part 4 I mean. So which values did we choose to be precise? We said at least 0.51 is precise, 0.51 also is precise, 0.50. Okay, let's look at the true value. The true value is 0.501. So at least even this one. These are the three precise values. So we need to find the mean. Mean is given as the sum of these numbers, 0.5020 plus 0.5105 plus 0.5112, and then you divide by 3. Let's see we are going to find here. 0.502 plus 0.5105 plus 0.5112. The answer we get, divide by 3. So the mean is going to be 0.5079. And then the second part is saying calculate the absolute error and standard deviation in the measurements. How do you calculate the absolute error? Absolute error is given by true value minus mean mass. So the absolute error, I can write ER, absolute error, that is going to be the true value. The true value we've been given, that is a 0.5010. We subtract the mean, that is 0.5079. So let's see what that gives us. So 0.510 minus the other number there, that is going to give us a 0.0069. Even if you find a negative answer, it should always be positive because this is absolute, and absolute means the answer that comes out should always be positive. The next one is saying calculate the standard deviation. How do you find the standard deviation? The formula for standard deviation, this is the symbol, so we squared, because sigma itself, this is the symbol sigma. Sigma itself represents actually sigma squared is variance. So standard deviation, we don't include this. Standard deviation, you can even write SD, is given by the summation of a value minus the mean. You square that, and then you divide by n minus 1. N minus 1, and then you square root your answer. Now, if you look at this question, what is going to be our, let's first find out what does x minus x mean stand for. What that stands for is you get a value, you get this value, you remove the mean, the answer you get, you square it. You get this value, you remove the mean, the answer you get, you square it. Get this value, remove the mean, the answer you get, you square it. All of these. And then after that, the answers that you're going to find, you're going to be able to add them. And then after you add them, so you are finding the sum of the squares. After you add them, how many numbers are these? These are 1, 2, 3, 4, 5. So n minus 1 means 5 minus 1. So 5 minus 1, that is going to give you a 4 down, and then you square root. But for this question, we are only using the values in part 4. Meaning we're only going to use these three values, this one, and this one. What you'll be doing is you get this first number, remove from the mean, the answer that you get, you square it. Get this second number, remove from the mean, the answer that you get, you square it. Get this third number, remove from the mean, the answer that you get, you square it. And then those answers that you are going to get after squaring, you add them. And then you are going to divide by n minus 1. So these are only three values, so it is 3 minus 1. So you divide by 2. And then you square root your answer. That is how you are going to be able to answer that. Number 4, give the name and symbol of the prefixes used with SI units to indicate multiplication by the following exact quantities. Now, the first thing that you need to understand is this. Let me write a 1 here. When I'll be moving up, so we are going to have 10 to the power positive 1, 10 to the power positive 2. We'll now start moving in multiples of 3. 10 to the power positive 3, 10 to the power positive 6, 10 to the power 9, 10 to the power 12. Even down, I'll go to 10 to the power negative 1, 10 to the power negative 2, 10 to the power negative 3, 10 to the power negative 6, 10 to the power negative 9, 10 to the power negative 12. These are the common ones you use. You can also talk about others. Now, 1 is a reference point. So 10 to the power negative, 10 to the power positive 1, that prefix is called a deca. 10 to the power 2, that is known as hecto. 10 to the power 3, that is a kilo. 10 to the power 6, that is uh, okay, 6, that is a million, so that is a mega. Power 9, that is a billion, that is a giga. Power 12, that is a trillion, that is a tera. And then coming down, 10 to the power negative 1, this one was deca, capital D. The ones on top are capital letters, capital D, capital H, capital K, capital M, capital G, capital T. These ones are going to be using small letters. 10 to the power negative 1 is a dec. 10 to the power negative 2 is a cent. Negative 3 is a milli. Negative 6 is a micro. The rest of these will be using their small letters, small d, small c, small m, but micro we don't use small, we use no, that's a symbol for micro. 10 to the power negative 9, this is a nano, small n. 10 to the power negative 12, this is a pico, that is small p. So if you look at 10 to the power 3, what is this one? This is a kilo. 10 to the power negative 2, what is that one? A cent. 0 0.1, 0 0.1 you can as well write it as this is 0 0.1. If you want to write it in base 10, all right? So of course you have got a 0 here, isn't it? So meaning this number is the same as I can move this decimal point from here. So be 1, 2, right? So meaning that 0 0.1 is actually the same as 10. Okay, I'll move the decimal point. Let me just move it once. Let me just move the decimal point once, because that's how you write numbers in standard form. So I'm going to move the decimal point once. It comes here. So it becomes 1 times 10. Now, how many times have I moved the decimal point? Only once. And I'm going to the left. So it is 10 to the power negative 1. Now, 1 times 10 to the power negative 1 is the same as 10 to the power negative 1. What is 10 to the power negative 1? That is a deci. Okay. And then this number here we've written is a million. A million is the same as 10 to the power 6. You have got 6 zeros in front, behind. So that is a mega. And then for this one, how many numbers are here in front? 1, 2, 3, 4, 5. Okay, so I'll write 0 0.1, 2, 3, 4, 5, and then a 1. So I move the decimal point 1, 2, 3, 4, 5, 6. So this number is the same as 1 times 10 to the power negative 6, which is just the same as 10 to the power negative 6, and that is a micro, right? So that is it for this one. And then the next one is saying provide a complete list of SI units. Now, what are SI units? SI units are units which are widely accepted to be used. Okay, and there are 7 primary quantities that we need to know, and their SI units. The first one is mass, and then you have also time, you have got length, you have got amount of substance, you have got current. What else? These are 1, 2, 3, 4, 5. So 2 more remaining. There is temperature, there is luminous intensity. So the sign for mass is a kg, time is a second, length is a meter, amount of substance, this is a mole, current is amps or ampere, temperature is Kelvin, luminous intensity is candela. So these are the SI units. Indicate the SI base unit or derived unit that are appropriate for the following measurements. So for a base unit, these are the ones that I've written on top. A derived unit is going to be found from more than one thing. For example, velocity is distance over time. Distance is in meters. Time, we know that SI unit is in seconds. So this becomes the derived SI unit. So if you look at the mass of your brain, if you look at the brain itself, okay, the mass of the brain, what do you think is the unit in which you are going to measure the brain? Because it is mass, this is kg, that is going to be the unit. The distance from your campus to your PHI-mo. This is distance. The SI unit for distance is meters. Your speed when coming to a chemist lecture, speed, as we said, is given by distance over time. Distance is in meters, time is in seconds, so it is going to be meters per second. The density of air, now density is given by mass over volume. Mass, the SI unit for mass is a kg. Volume is length times length times length. You are multiplying length 3 times, so that will be meters cubed. So the density of air is going to be kg per meter cubed. The area of the chemistry laboratory, area is given by length squared. Length is given in meters, so that will be meters squared. The volume of a cholera shot, now volume is given by length to the power 3, and length is in meters, so that will be meters cubed. The blood concentration of glucose is 180.16 gram per mole. In a patient, is found, okay, the blood concentration of glucose in a patient is found to be 5.1 millimoles per liter. Express this concentration in the following units. You want to express it in grams per liter, in percentage, that is mass, percentage mass by volume, in parts per million, that's ppm, in milligrams per deciliter, and these others. So to start with the first one, we want to express the unit in grams per liter. Now look, already you've been told that glucose concentration, this number in brackets, is 180.16 grams per mole. Now I want the answer in grams per liter, so I don't want the mole in the denominator. But also we have found out that the concentration is actually 5.11 if it is in millimoles per liter. That is millimoles per liter. So what am I going to do here? I'm just going to multiply these two numbers. Okay, I'll just multiply these two numbers. That is 5.11 millimoles per liter. And the reason for that is that this mole down can cancel with the mole that is on top there. So that will give us our answer remaining in grams per liter. But here, this is a mole, this is a millimole. So I need to convert a millimole to mole. So I'm going to multiply. I've got a millimole on top. I'm going to put a millimole down because I want it to cancel. And then I want to convert to moles. A mole and a millimole, which one is bigger than the other one? A mole is bigger than a millimole. Remember the units that I had written earlier? Milli means -3. But because I have put a 1 in front of a bigger unit, I'll just use +3. So this millimole will cancel with a millimole. Mole will cancel with mole. So the answer will now remain in grams per liter. So let's just multiply this. This is 180.16, and then we are multiplying it by 5.11, and then we are dividing it by 1000. So approximate is going to give us 0.920 grams per liter. And then for B, it's saying we want to find the percentage mass by volume. Percentage mass by volume. In other words, on top we want to have the mass, down we want to have the volume. Already for this unit, you can see this is mass, right? And then this is volume. That is percentage mass by volume. But just something that you need to know about percentage mass by volume is there is an unit in which you express it. Okay. So when you are finding the percentage weight by volume, you need to make sure that your weight is in grams. Your volume should be in milligrams. That is how you find percentage mass by volume. So I'm going to get this number. It is already grams per volume, 0.920 grams per liter. Now the liter should always be in the volume should always be in milliliters. So I'm going to convert. I'll multiply. I've got a liter down. I'm going to put a liter on top because I want to cancel liter. I want to go to milliliters. Okay. In 1 liter, a liter is bigger than a milliliter. So I'm going to put a 1 in front of a liter. Milli, that is going to be 10 to the power 3. Now, liter can cancel with liter. So the answer will now remain in gram per milliliter. Now, percentage mass by volume. This is a percentage. So the answer that is in gram per liter is supposed to multiply it by 100%. That gives you percentage mass by volume. So this 100 can cancel with this 1000. So you are going to remain with a 10 here. 10 into 0.9. So that will give us 0.092% mass by volume. So that is going to be the answer there. And then the next one, I want to find the answer in now parts per million. In parts per million again, all you do is get your answer, you multiply by a million. A million is 10 to the power 6. Okay. And then also in milligrams per deciliter. Milligrams per deciliter. The answer is already given. This answer that you can see is 0.920. It is in grams per liter. Just convert it to grams per deciliter. So what are we going to do? I'm first going to convert a gram to milligram. So I'm going to multiply. On top I've got a gram, down I'm going to have a gram. And then on top a decigram because I want to go to decigrams. Deci, all these units which are down here, it means they are smaller than the unit without any prefix. What I mean by no prefix is gram, you can see there's no anything in front, different from decigram. So a gram is bigger than a decigram, so I'm going to put a 1 in front of a gram. Deci means 10 to the power negative 1. Because I've put a 1 in front of a gram, I'll use a positive 1 because gram is a bigger unit. This gram will cancel with this gram. And then again, I'm going to multiply. We have got a liter, I want to convert it to deciliter. So I'm going to again, there's a liter down, I'm going to put a liter on top and then deciliter down. A liter is bigger than a deciliter, so I'll put a 1 in front of a liter. Just remember it is 10 to the power negative 1, but because I put a 1 in front of a bigger unit, so it becomes positive 1. So if you just multiply this 10 will cancel with this 10. This liter will cancel with this liter. So the answer will still be 0.92, but it is now in milli. Actually, this was supposed to be in milligrams. I used decigrams. So here we will need it to have milligrams, not decigrams. So milli means 10 to the power positive 3. So this is what we should have used. Okay, so we're going to multiply 0.920 times 10 to the power positive 3 divided by 10 to the power 1. The answer that you get is going to be your answer in milligrams per deciliter, and that is going to be like a 92 milligrams per deciliter. So that is how you are going to go about question number 7. Number 8, a piece of a fake engagement ring has a mass of 26.52 grams. A graduated cylinder initially contains 9.72 milligrams of water. And then the question is saying when the ring was dipped. Okay, so we need to understand this. The volume of water before the ring being put in it was 9.72 milliliters. When we put this ring inside the water, the volume, that is V2, had to go all the way to 12.24 milliliters. The question is, determine the density of the ring in grams per milliliter. 3 significant figures. So first thing first, we need to find the volume of the ring. Volume of the ring is going to be given by V2 over minus V1. 12.24 minus 9.72. So let's see what that is going to give us. 12.24 minus 9.72. That is going to give us, okay, just a moment, 12. This is a 12.24 minus 9.72. This is going to give us a 2.52. The answer, remember, is in milligrams. Now, we want to find the volume. And you know that the volume is sorry, not volume. The question is asking us to calculate the density. Density is given by mass over volume. And the mass of this ring, they've told us it is 26.52. It is in grams. The volume we have just calculated to be 2.52. It is in mils. So if we divide, so 26.52 divided by what is down there, that is going to give us 10.5238. The numbers continue to go grams per mil. The answer is saying you leave your answer in 3 significant figures. So 1 here is significant, 0 is significant, 5 is significant. So we are going to end at 5. Because this number is below 5, we'll not remove any number from it. So we'll not remove a 1 from it. So the answer will be 10.5 grams per mil. Assuming the ring is made of only a single element, what element is it? So we want to check what element has got this density, 10.5 grams per mil. So we'll go on this table, the density of 10.5 grams per mil. Now, if you look at the densities given in this table, their densities in grams per liter, not per mil. So, if you convert this density, 10.5 grams per mil to grams per liter, just multiply. We have a mil down, we'll put a mil on top, and then a liter down. A liter is bigger than a mil, so I'll put a 1 in front. 1 liter has got 10 to the power 3 mils. So this mil will cancel with this mil. So 10.5 times 10 to the power 3, the answer is going to be 10,500 grams per liter. So this is the density, 10,500 grams per liter. So let's try to go for those values. 10,500 grams per liter. So it can't be anything this side. So it is actually this one here, because a centimeter cubed is the same as a mil. So 10.5 grams per mil is the same as 10.5 grams per cubic centimeter. So the answer there is silver. So this was the silver. In less than a half handwritten line, explain your answer in part 2. Now, why the answer that we have found in part 2? Why have we said that this element is silver? So the calculated density matches with the density of silver that is known, indicating that the ring is silver. Alright, so that is it. Question number 9. Give the correct answer to each of the following equations with the correct number of significant figures. So the first one we have is 4.26 plus 3.831. So if we get to add this, let me add first 4.26 plus 3.831. The answer that we find here is 8.091. Now, the rule of addition is when you add two numbers, the answer that you get, you are going to write it to the same decimal places as the number that has got the fewest decimal places. So you can see this one has got two decimal places, as this one has got a 3. So the final answer should only have two decimal places. So therefore this is going to be 8.09. That is going to be the final answer. And then for the second one here, number 2, what you want to do is first to divide and then subtract. Now you know the rules of mathematics, the board math. If you have got, actually this is not a division, that's an addition. So we are going to add these numbers. So that is a 16.262 plus 4.33 minus 0.40. The answer that we have gotten here is a 20.192. Look at the number with the fewest number of decimal places. This is 3, this is 2, this is 2. The final answer should have only two decimal places, meaning that the answer is going to be 20.19. Okay, like that. For this other one, we are multiplying 63.8 times 0.80. 63.8 times 0.80. The answer we're going to get is 51.04. Now, the rule for multiplying is when you multiply two numbers, the final answer should have significant figures, the smallest number of significant figures as the number with the smallest. So this one, how many significant figures are there? 3. How about this other one? This is 0 significant. The 0 in front of the number which has a decimal is not significant. This one has got 2 significant figures. This one has got 3. So you follow significant figures, the one with the lowest. So the final answer should have only 2 significant figures. So therefore, 2 significant figures for this number is 51. Okay, 1 2. If I just put a decimal point here and write anything this side, I've changed things. Okay, so it's just a 51 without any decimal. And then for the other one here now, we are first multiplying 58 sorry 53.8 times 0.9. The answer that we get, we are dividing it by 0.3025. So the answer that you are going to get for this one is a 160.0661157.248. Now look at the significant figures. Which one has the fewest number of significant figures? This is a 3 significant figure. This is 1 significant figure. This is 4. So the answer should have only one significant figure. And one significant figure meaning that you only need to have this one as the only significant figure. So what are we going to do? We are going to write this as, we're supposed to have like a 1 there, right? 160 like this. Now, one significant figure, we're supposed to round off. Look at the number that comes before. We're going to remove a 1 from it and put where there is 1. So that will become 2. Where there was 6, put a 0. And then there was another 0, put it there. I could have just written a 2, but that changes the number. So this number is in a range of hundreds. That's why I've decided to add these two zeros there, because it was in a range of hundreds. So this number has got only one significant figure, that is a 2. Okay. Write the values of measurements in question 4, part E and G in scientific notation. Question 4, part E and G in scientific notation. We had actually already written in this one. This one is 1 times 10 to the power 6. This one down here, we had said it was 1 times 10 to the power negative 6. So that is it for this paper, and those are the solutions. In case you want to register with Acidis Academy for online classes, you can get to contact us on 0974 016268. And the courses available, there's mathematics, biology, physics, and chemistry, you can get to WhatsApp us or give us a direct call, and then you'll be made aware of the academy and everything. Thank you so much for having watched. Enjoy your day.